continuing with limits. So on Tuesday, we talked about limits as x is going to some number. And we did
I can hear you. I'm doing my class.
a little bit. I'm gonna mute you. We did a little bit talking about asymptotes, and today we're going to talk more about asymptotes. So, section 2.2 is titled Infinite Limits and Limits at Infinity. So these are limits that deal with infinity in some way. And I'm going to scroll down. So here is our first question. So on Tuesday, we were saying that whenever we had an asymptote, the limit did not exist. And that's still technically true, but I said don't get too attached to that because we have another way to express limits when we're dealing with asymptotes. So we're going to start by just looking at this graph. So we're going to use this graph of f. So this blue part is our function f of x, and I just put that red dotted line to show that there's a vertical asymptote there. So we are going to use this graph to determine the following limit. So let's start with a. So x is going towards 0 from the left. So remember that little minus sign says we're coming from the negative side, which means we're coming from the left. And so we want to know what is happening to f as x gets close to 0. So on Tuesday, we would have said it does not exist, but now we're going to use a different way to express what's happening here.
It's increasing.
Yes, it is increasing, and that's important. It's increasing forever and ever and ever and ever.
So infinity increase?
So infinity is actually what we will say as our limit in this case. So since if we're on this graph, if x is getting closer and closer to 0, our function value is just going to keep going up forever. So it is increasing infinitely. It's going to go up forever, which means that we're just going to say that the limit as x approaches 0 from the left is infinity.
And we don't have to put like infinity plus or infinity negative, right? Just infinity.
Well, if it's a negative infinity, we do have to put a negative infinity. So
okay.
This is positive infinity since it's going up, so we don't have to put a plus because just infinity implies that it's positive.
Positive.
Yeah, we will see that in a little bit though when we have to use a negative. So technically, this limit still doesn't exist because it's not going to a number, it's going to infinity. But we still use infinity to express where it's going. So this is basically saying that it's increasing forever. So it's going toward infinity, even though it'll never reach it because that's not possible. So let's look at our next two parts. So part B, we want to know the limit of f as x approaches 0 from the right. So this little plus is telling us we're coming from the positive side from the right. So in this case, f, we're getting close to 0 from the right. So what is the function doing in this case?
Infinity.
Exactly, it's infinity again. So this is this is what asymptotes do, right? When the function gets close to an asymptote, it keeps getting closer to that asymptote, but it has nowhere to go other than either up or down forever, because it can never actually get to the asymptote. So anytime we have a vertical asymptote, the function is going to get close to that asymptote and either go super far up or super far down. So in this case, both sides are going up to infinity. So we have one more question here. Limit of f as x approaches 0. So this time it doesn't say either side, it's just saying approaching 0. So we can think back to how we talked about limits on Tuesday. So what do you think we will write here?
Does not exist.
In this case, we're not going to say it doesn't exist. It's true that technically there is no limit, but we are going to express it in this.
Would it be like undefined?
Not quite.
Infinity?
It's still infinity.
Okay.
And that's because last Tuesday, this Tuesday, we had the definition of limits is that the limit exists if and only if we have the same limit coming from both sides. And in this case, it's a little weird because we're not actually going toward a specific number. But since both sides are going to infinity, we say that the limit of f as x approaches 0 is infinity, since both sides are going to the same place. So this part C comes directly from parts A and B. So both one-sided limits go to infinity. Oops.
So I'm pretty sure we're going to cover it today, and that's probably going to come after this. But if one was going down and approaching 0 to infinity, would we still put infinity?
So you are right that we are going to cover it.
Okay,
But
then.
So this part C is specifically going to infinity because both sides are going to infinity. They're going to the same place. So you're actually describing exactly what our next example looks like. So before we go on to that, let's just review what we're seeing here one more time. So on this one, from the left, as the function gets close to 0, it's going up forever, which means it's going toward a positive infinity, or just infinity. From the right side, it's also going up forever, so it's going toward infinity. So since those right and left limits are going toward the same place, we can say that the limit going to 0 is also infinity. So let's look at what if we have an asymptote where our functions our two sides of our function are going at these 3 questions. So these are actually the same 3 limits. We just have a different function now. So now we have this green function g, and there's still a vertical asymptote at 0. So take a moment to think about these 3. Okay, so on this one, our part A, the limit of g as x approaches 0 from the left.
Negative infinity.
Exactly, negative infinity. So this time, our function is just going down, down, down forever as it approaches 0 from the left side. So since it's going in the negative direction now, it's still going to infinity, but it's negative infinity. So how about from the other side, approaching 0 from the right?
Positive infinity.
Yes, exactly, positive infinity. So that side is going up. And we can just write infinity. So in this case, both sides are going in different directions. So what do you think for the limit as x approaches 0?
Quick question, do we use, is unions a part of this?
No, not for limits.
Okay. So negative infinity to infinity?
Undefined.
Because of the horizontal
Oh.
Is
asymptote?
it D and E because they go to different places?
That's
That's it, yes, they go to different places. So hold on to that horizontal asymptote part because that will be coming later.
Okay.
But for now, as x is approaching 0 from both sides, they go to different places. So we can't say that there is a limit because one part of the graph is going one place and the other part is going a totally different place. So in this case, we do say D and E. So that's the same as on Tuesday when we had those graphs like piecewise functions where one side is going to one value and the other side is going to another value. We say the limit doesn't exist because both sides are going to a different place. It's the same thing here. It's just they're going to a different kind of infinity. So if we have both sides going toward the same place, we can say that their limit is that. The limit as x approaches the asymptote is infinity. If they're going to different places, we have to say that just the regular limit doesn't exist since they're going to different places. Was someone else about to ask a question?
I have a question about the homework.
Ooh, what is it?
Well, so on problem 15, it has a graph and it says x limit 2 to the negative. And in the back of the book, it says the answer is 1, but I don't understand how they're coming up with 1 because it's on 2.
Problem 15, so A,
Uh-huh.
it is 1. So just as a quick refresh of last week, or last Tuesday, I don't know why I think it's last week. That function looks like And there's another holder. So if we're looking at the limit, as x approaches 2 from the left of this function,
Oh. Okay.
we are approaching
I was looking at -2. That's why I was.
2 from the left, which means we're traveling. Yes, so this little
Okay.
negative up here just means from the left, but since there's no negative in front of the 2, that is a positive 2. So that will be equal
Okay.
to 1.
Thank you for clarifying.
Yep.
All right. Sorry, guys.
So yeah, and those little negatives and positives can be confusing because they're not actually saying something is negative or something is positive. It's just indicating a direction. So it can be tricky to get used to this notation of having those little pluses and minuses.
So the function is moving towards 1, or is that as it moves towards 2?
It's moving toward 2, the x value of 2 from the left. So it's going to 2 from the left, which means the function is going toward 1. So the function value here is 1. Piece of this piecewise function, if we're going toward 2 from the left and we follow that function, we're going toward that point where x is 2 and y is 1. It doesn't get there because there's a hole, but the underneath the word lim says what x is going toward, and our answer is what is y is going toward. So y is getting close to 1 there. So on Tuesday, so this is from section 2.1, we were looking at things where we were going toward a certain point, but now we're looking at things where we're going off to some sort of infinity, which are asymptotes. And my cat is trying to steal my mouse right now. Feels like a joke. Okay, we're fine. Okay. It is. He just wants to play. Okay, so we're going to do another example with these kinds of asymptotes, but this kind of limits, these are specifically infinite limits, where where our function is going toward infinity in some way, which are often vertical asymptotes, but not always. We'll see some other examples in a bit. So let's look at one more example. So those are directly from the graph. On these ones, so most of our limits, I want you to be able to do it algebraically, or at least see how to find them algebraically. Last class, we were plugging in numbers to find our results. For these kinds of infinite limits with vertical asymptotes, you can graph it as well to get an idea of what we're looking at. So this is going to be our next example. We have f of x equals x over x minus 4, and we have 3 limits. So I am going to let you look at the graph of this and do it from there. But first, I just want to talk about another way that we could look at these without graphing. So we know from algebra that there is an asymptote at x equals 4 here. Because this is fully reduced, x over x minus 4 is not going to reduce anymore. So that denominator is telling us that there's an asymptote at 4.
Do we have to figure out what kind of asymptote it is?
We know, well, we can tell that it is a vertical asymptote because only vertical asymptotes come from the denominator. We are going to talk about horizontal asymptotes today, though, but it will be a different kind of limit. So I'm pointing out that we have an asymptote at x equals 4 because each of these limits is looking at what's happening as we approach 4. So we know that we are dealing with a vertical asymptote. Vertical asymptotes, ooh, I just remembered that I skipped something. I got distracted by my cat. Let me just go back for a moment to this last little bit about vertical asymptotes. Oops. So if we have a vertical asymptote at x equals a, so it could be any vertical asymptote, then the right and left-hand limits of f as x approaches a are either infinity or negative infinity. So I'll give you a moment to take that down. So this is really what vertical asymptotes are. When we first learn about them in college algebra or pre-calculus, we learn that the function can get close to them, but it can never touch, which means the only place it has to go is either toward infinity or toward negative infinity. And so the limit, if we're ever getting close to any kind of vertical asymptote, the function has to either go to infinity or negative infinity, and it can go to different places on either side, but those are the only two places it can possibly go. So here we have an example where one side is going to infinity and one side is going to negative infinity. Up here we have a side where they're both going to infinity. They could both be going down also. So either way, and then anytime we have a vertical asymptote, we know that if we're looking at a limit going toward that, our answer will be either infinity or negative infinity. We just have to figure out which one it is. So that's our important piece of information for this example. So we know we have an asymptote at 4. So we're looking at our limits as we get close to 4. First from the left side, then from the right side, and then together. So each of these either has an answer of infinity or negative infinity. And that's really the question we're answering. Which way is it going? So we could figure this out from a graph, which you can do, but I just want to show another way to do it, which is to just take some values of x and put some values that get closer to 4 from the left. So that could be, I might just try like 3.5, 3.9, 3.99. And we don't need very many. Basically, all we're trying to figure out is that, is this increasing, so it's going towards infinity, or is it decreasing down to negative infinity? And I don't have a calculator handy on here. Let's open this. So our function is x over x minus 4. So if we plug in 3.5, we'll get 3.5 over 3.5 minus 4, which is 3.5 over negative 0.5. And if we put that into a calculator, we will get negative 7, excuse me. Could have done that. And if we try this for each of these values, oops, I didn't make a very good table here. 3.9 over 3.9 minus 4 will be 3.9 over negative 0.1, which will be negative 39. And if we plug in 3.99, we'll have 3.99 minus 4, which is going to equal 3.99 over negative 0.01, which will be negative 399. So all we're doing here is taking these values of x that are getting closer to 4, specifically from the left side, since that's the limit we are looking at, and plugging them in to see what's happening to the function. So we started off with negative 7, negative 39, negative 399. So we can see that the function is getting bigger in the negative direction as we get closer to 4 on the left.
So for the test numbers in the table, did you pick numbers that were like just below and like right below 4?
Yes, exactly. So they should be like pretty close to 4 and then just getting closer to 4. And below specifically because this one is approaching from the left side, so they have to be a little smaller.
Could you do this test table for the one that's with the positive moving right too, but would the numbers be like above instead?
Yes, exactly, yeah. So they would be coming at 4 from the right side. And so here we're seeing that these are getting bigger in the negative direction. So that means that this limit is getting closer to negative infinity. So we know that that limit is going to negative infinity. And so this might feel a little tedious, taking values and plugging them in, but it's a way that we can do this, the way we can analyze the graph. And we could do the same thing for B, which I'm just going to copy. Just going to move it actually. So yes, as was just said, here we could take some values of x and plug them into f of x. And this time we just need some values that are close to 4 and above 4. So if I'm kind of coming at it from the same angle, I could start at 4.5, then maybe 4.1, 4.01. They just have to be getting a little bit closer to 4. And there's no like exact way to choose these. You just shouldn't choose numbers like 10 or something like that, because that's pretty far away from 4. They should be reasonably close to 4 so we can see what's happening when we get close to that asymptote. And so if we plug in 4.5 into our function, we will get 9, 41. I made a bad table again. So in this case, we can see that our numbers are getting bigger. And they're getting bigger in a positive way. All of them are positive. So here we are going toward
Infinity.
exactly. So our limit in this case will be infinity. So we know there's an asymptote there, which means that we're definitely going toward either infinity or negative infinity from either side. So this is just one way to find out which infinity we're getting close to. And so when we look at part
Process of
C,
elimination.
yes, so I got a little disorganized here. I'm gonna move this down below so this makes sequential sense. So if we're looking at our limit as x approaches 4 and we don't have, or a minus on here, we have to use what we know from parts A and B to make our conclusion for this one.
And that'd be the D and E.
Danny.
Yes, exactly. Why is it DNE?
One's going
One's
down.
going up, one's going down.
Yes, you have the exact same explanation. Yeah, one's going up and one's going down. So they're going to different places. So the right and left limits don't match.
Will there ever be a case that they go in 2 different directions and it's not Danny?
No,
Okay.
it always will be if they're going in different directions. Okay. So I want to do one more like this, but this time I would like to do it by graphing instead of the tables. So this table method is one way to do it, which you're welcome to use. Let's look at one more example. So here's our So go ahead and graph this function either in Desmos or on a calculator. So you can see what the graph is doing around the asymptotes.
The connection is kind of bad today.
Yeah, I keep getting a little, your connection is unstable alert.
Yeah.
If ever it is bad and you can't understand me or anything, please let me know so I can say it again. Or I was talking to another colleague yesterday who also has CenturyLink, and she said she was having the same issue this week, and hers is hardwired. I'm on Wi-Fi, but even she was having issues. So
Wow.
I don't know.
I have Suddenlink and it's not as bad.
Mm. Okay, so if you are looking at this on a graph, either Desmos or a TI, I'm gonna try something that I have not tried before. See if I can share this. Oh, I can. That's great. Okay. So here's what this graph should look like on a calculator. So I put in the y equals section, our negative 4x divided x plus 3 squared. And so we can see on a graph, we have an asymptote at -3, a vertical asymptote. And this one isn't showing it super steep, but we can see both sides are going toward the asymptote from either side. So if you put it into Desmos, it should look something like this. And be super careful also to have parentheses around the denominator. That's one thing that can mess up entering. So on our graph, we can see our limits now. So we could still make a table if we wanted to. But what is the limit as x approaches 3 from the left? -3, excuse me, -3 from the left.
Infinity.
Exactly, it's coming up and going towards infinity. And how about -3 from the right?
Infinity.
Exactly, still infinity, since they're both going up when they approach the asymptote. And there's one thing, we do have one more, but another feature of this calculator that I want to mention is that on the button graph, if we look at just above it, it says table. So if I do y equals, or excuse me, not y equals, stop that. That's not what I meant to do, sorry, okay. If we do second table, it will show values, it will show values of x and their corresponding values of y. So I can go up and get closer to -3. And we can see when it's actually at -3, there's an error because that's an asymptote. But then we can also see as we get close to -3 from the left, it's getting to be bigger numbers. And as we get closer to -3 from the right, it's also getting bigger. So this is kind of the calculator making that table that we were doing in the previous example for you. This is not a necessary thing to look at, but it's something that's there if you want to use it. So in all of these methods, we're just trying to get some idea of what direction our function is going as it gets close to that asymptote. So let me switch back. here. So we said as x approaches -3 from the left, we have infinity again. As x approaches -3 from the right, we have infinity. And so what is our answer for the limit as x approaches -3?
Danny. No.
Infinity.
Infinity, yeah. Since they
Um,
match. So in this case, they're going the same direction, so it will be infinity here. So on that last one, we're just looking to see if those two sides we started with are the same or not. So here we did this by graphing and just a super rough sketch of that graph. If here is our asymptote at -3, our graph was doing something like this. I don't remember exactly what it looks like, but something like
that looks
that.
good.
Thank you.
So on the first problems that we did on C, when x was going towards 0, it was infinity.
Yeah, so looking back
Oh,
from
I was
first
looking at the
couple.
second set. My
Yeah,
bad, I was
so
looking at one.
that's okay. So the first one we saw they're both going to infinity, so we say the regular limit is infinity. The second one, they were going opposite directions, so we said the limit does not exist.
Okay.
So I want to put together these two things that we did on Tuesday and today before we go into our next kind of infinite limit. And so here we have a rational function, and these are three limits that we want to find. So I'm going to give you a minute to look at that and think about how we will go about finding these three limits. So we're putting together Tuesday stuff and today stuff now into one example of a rational function. So we're looking at the limit as x goes towards 3 and -2 from either side. So the first thing we should try to figure out is what is happening on the graph at that place, because that will give us an idea of what kind of a limit we'll be dealing with. My recommendation would be to simplify first. So the denominator, x squared minus x minus 6, will reduce to x minus 3x plus 2. Or will factor, excuse me. And then we can cancel that common factor. So the thing that we're left over with, that leftover denominator, gives us our asymptote. So this is the kind of thing we were just seeing. So in our simplified version, the denominator will tell us that we have an asymptote. So since we have an asymptote at -2, and we can see that this x minus 3 canceled. So there's a hole at x minus 3. X equals 3, excuse me. So we saw a situation at the end of last class where the thing that canceled was actually still left over in the denominator. So we should look at the asymptote first. Whatever is left over in the denominator is definitely an asymptote. And if something else canceled, then we have a hole there. So on part A, we are trying to find the limit of f as x approaches 3. So that's the hole. How do we go about finding that limit?
Plug 3 in for x.
We will plug 3 in for x. Where should we plug it into?
Into the reduced fraction.
Yes, exactly. We'll plug 3 into the reduced version. And we get 1/5. So that's a part of a graph where it still looks like a regular graph to the naked eye. There's just a little piece missing right at 3. So our limit is still going to a specific value right at 1/5. So then parts B and C, we know that -2 is a vertical asymptote. So we just have to decide what infinity each of these is going toward.
So would you plug -2 into that same equation?
So if we plug -2 in to even our reduced version, we'll get 1/0, which we don't want.
Oh,
So we can't plug in -2.
Can you just plug in numbers that are slightly smaller or bigger like we were doing
Bigger.
last time and then just look for it?
Yes, exactly. That is one way to do it.
or graph it on Desmos.
Or graph it. So methods for B and C. I'm actually going to give one more method just for variety. You can choose which one. So we can graph. We can make a table. Or we can just do a little bit of analyzing to decide if our function is going to be positive or negative on that side of the graph. So by that, I mean, we can use the reduced version because the only difference between these two versions is that whole. So the reduced version is the simpler one to work with. So if we're doing part B first, we are looking at what happens as we get close to x is -2 from the right. So if we think, okay, we know that x is going to be greater than -2 because we're approaching it from the right. If x is greater than -2, then x plus 2 is positive. No, yeah, that's right. I have to think for a second. So for example, if x was -1, that's bigger than -2, and -1 plus 2 is positive. So it's just a little bit of thinking about if x is on the right side of -2, it's bigger. So if we add that to 2, we'll get a positive number, which means 1 over x plus 2 is also positive. So it's never going to be a negative number as long as we're on the right side of 2, because we have a positive over a positive, which means it's going to positive infinity. So when I say we can analyze to determine whether it's positive or negative, this is what I mean. We can just think about, is this thing going to be positive or negative when we're on one side of 2? -2. And so we could think of this the same way on part C. If, in this case, we have x is less than -2, because we're approaching -2 from the left side. So we're always going to have values of x that are less than -2. Then that denominator, x plus 2, is actually going to be less than 0, because we have some negative number that's more negative than -2, like -3, -2.5. So 1 over x plus 2 in this case, 1 is positive, so a positive over a negative is negative. So in this case, we have negative infinity. Each of these is just an option. So you can graph it to figure this out. You can use a table to figure it out, or you can do a little bit of logic like this to figure it out. And it is up to you. I just want to give some options and a little bit of context to see different ways to look at these limits. So any of these infinite limits, you can make a graph, you can make a table, or you can do a little bit of analyzing. Is this positive or is this negative?
And you'll accept any one of those or any one of those as work?
Yes.
Okay.
Do we have to say which method we used?
Yeah. I think if graphing is the only one that you wouldn't have something written down. So if you graphed it, you can say by the graph, or I graphed it, or something like that. If you make a table, then that should be in your work. Or if you do this analyzing, that should be in your work too. And these infinite limits, these ones that are going towards infinity or negative infinity, are the only ones that I want to, that I'll accept graphing as an answer. All of the other ones can be done algebraically, like this one. We reduce and then plug in.
Is it a good habit to get into, or should we get into the habit of factoring and like simplifying the equation first before plugging anything in? Or does it just depend?
I think it's a good habit if it's possible to do so, because then you can see it's more obvious where the asymptotes are, what a hole is, and the reduced version is usually just easier to work with.
That makes a lot of
We
sense.
have
Okay.
less stuff going on. Yeah. So it won't hurt you to try to do some stuff first, but yeah, simplifying is usually useful. So this example was taking things that we did on Tuesday and today. So when we have a rational function like this, we know that weird things happen when the denominator is 0. So in this case, we had a hole, which we can find a limit for, and we had a vertical asymptote. But there are other things that rational functions do, and not just rational functions. But in all of these examples so far, x has been going towards some number. It's been going toward a hole or an asymptote or just a regular point. X can also go toward infinity. So that is the second part of this section, limits at infinity. So this part, I'm going to put up a poll in just a moment. So I want you to first, just on your own, think about these two questions. And I'm going to put a poll for part A before we talk about it. So here is a graph. So notice that this time the horizontal asymptote is the one that's highlighted, that little red dot. And we want to know what happens to the function when x is going towards infinity and when x is going toward negative infinity. So I'm going to put the poll, and just remember the limit is always on the bottom. We have what x is going toward, and our answer is always what y is doing. So I'm launching the poll now, and it's multiple choice. And I can't draw infinities on the poll, so I wrote out the words infinity and negative infinity. So I'll give it about 30 more seconds. There's no calculations involved here. Just what is your notion? So this will be part of your in-class activity today. So if you haven't chosen something, do so in the next few seconds. Okay.
Is there any way to
nice and
change your
ending
answer?
poll. There's not, unfortunately, I don't think. Okay, ending the poll. So about, so 59% chose 0. A few chose 1. We have some votes for infinity and some votes for negative infinity. So before I say which of these answers is correct, let's look at what's going on here. So x now is going toward infinity. If x is going towards infinity, that means x is going this way. So we want to know what's happening to the function when x is going towards infinity. So when x is going towards infinity, the function value, the y value, is getting closer and closer and closer to something. 0, yes. So 0 was the correct answer here. Because our actual graph is going down, 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 and it's continuing to decrease forever and ever. But it's never quite getting to 0. So that's what the horizontal asymptote is saying. The function is getting closer and closer and closer to 0, but it never actually reaches it. But it's still going that direction forever. So the limit as x goes to infinity of this function that's graphed here is 0. So I'm going to launch a next poll for part B. So I'll give a little less time for this one since we talked about A.
Are these limits always just normal limits, even though you can only really evaluate them from one side since the other side's infinity?
Yes, so these
Okay.
ones we don't have the two-sided notion because x, there's no other side of infinity. So yeah, they're always just regular limits, not the right side or left side.
Okay, cool.
Yeah, that's a good question. So about 10 more seconds. Okay, closing the poll. No. Okay, so this one, so we didn't have any ones or infinities this time. So on this side, x is now going toward negative infinity, which means that x is going this way. So as x goes to negative infinity, our horizontal asymptote is still dictating what the function is doing. The function is getting closer and closer and closer to that horizontal asymptote, which means that the function is going towards 0. So 0 is the correct answer again here. As x gets closer to negative infinity, the function is closing in on 0 forever.
So I'm understanding the concept of it's getting closer to its number. So like if the horizontal asymptote was like one line above that at 1, and the line was still doing that, it would be 1, right, instead of 0.
Yes, exactly.
Right.
Yeah, so anytime we have a horizontal asymptote, and we are gonna tie this into horizontal asymptotes in a little bit, but yes, a horizontal asymptote is the limit as x goes to infinity or negative infinity, because that's what the function is doing as it goes out forever. So We have one more graph. This one does not have a horizontal asymptote. And I'm just going to add one little bit to this graph just to make it more clear what it's doing. So this is a degree 3 polynomial, which means it's going off in that direction and off in this direction. So those aren't ends, they're continuing. So we have basically the same question. What is happening as x goes to infinity and x goes to negative infinity? So I'm going to put up another poll. So the first question is, what is the limit of g, this new function, as x goes to infinity? So again, the question is, what is y doing when x goes to infinity? Okay, and I'm going to close in a couple seconds. Okay, so here we have most answers of infinity, and that is correct. So in this case, as x is going to infinity, so if x is growing, y is also growing. It's getting super steep, so y is growing faster than x at some point, but it's still going up. So as x increases forever, y also increases forever. So infinity is correct here. So let's just have one more poll of our last part. Last poll of the day. So what's happening to g when x goes to negative infinity? Okay, ending the poll. All right, and just about everyone said negative infinity, and that's correct. So on this one, on the left side of the graph, as x is going down towards negative infinity, the graph is decreasing. So in this case, rather than looking at horizontal asymptotes, we're really just looking at the end behavior of the graph. So end behavior is something that comes up in college algebra and probably pre-calculus, where polynomials have certain end behaviors. Both of their ends are either going up or both down, or they're going in opposite directions. And that is really what the limit at infinity is referring to here. On this one, the graph is increasing, so when x goes up, y also goes up, and when x goes down, y also goes down. So we're going to focus mostly on rational functions in this section as well, but just as a quick overview of polynomials. So limits at infinity of polynomial functions, which really is just another way to express end behavior of polynomials. So these questions that are on here, we want to know the limit of this function as x goes to infinity and negative infinity. We don't have to do any plugging in or anything here. We just need to have an idea of what this polynomial looks like. And that is fully based on the leading term. So the leading term is the one with the biggest exponent. So this polynomial is degree 4. Its leading term has an exponent of 4. So if a polynomial has an even degree, does that mean that both ends are going in the same direction, or does it mean that the ends are going in the opposite directions?
Same direction.
Yes, exactly. Anytime we have an even degree, both ends are going in the same direction. Like a parabola, that's a good reference for an even degree. So if we have a positive number in front of our leading term, a positive leading coefficient, does that mean that both ends are going up or both ends are going down?
Up.
Yes, exactly. So that is all we need to know. It's going to be something like this. Fourth degree has a maximum of 3 turns. But all that we really care about is that both ends are going up. So even degree, both ends go in the same direction. And a positive leading coefficient. Means they're both up. So just knowing the general shape, we don't have to graph this into a perfect graph of this particular function. All we need to know is that it's even and has a positive leading coefficient. So what does that say about our limits as x goes to infinity and negative infinity?
They're both positive because it's both going up.
Exactly. They're both going toward positive infinity because both sides are up. So we don't need to know what the zeros are. We don't need to know exactly what perfect squiggles are happening in the middle. All we need to know is that both ends are up. And that tells us we have positive infinity for both of these limits. So how about this one?
Down.
Down, so we have a negative leading coefficient. But we also have a 5th degree here. So which side is down?
The left.
Like this?
Yes.
It's actually flipped the other way. The right side's down and left's up.
Yeah, it will actually be flipped here. So in this case, don't know why I used red over there. So we have an odd degree, which means that either we have, or we definitely have one side up and one side down. So it's going to be one of these two choices with some number of squiggles in the middle. But the leading coefficient If it's positive, it's going to be this increasing version. And if it's negative, it'll be this decreasing version. So these are the two possibilities we have for an odd degree function. And I drew those super rough, but the point is that one side is going up and one side is going down.
So if it's a negative coefficient, it goes down.
Yes. So this one is decreasing. So if we look at it left to right, it's going down, and it'll do some ups and downs in the middle, but eventually it'll keep going down.
So if that 2 was a positive, then it would be the one on the left.
Yes, exactly.
Gotcha. Okay.
So all we need to look at again is that first, or the order could be different. So it's not necessarily the first term, but it's the term with the highest power. We need to look at that power to decide if it's even or odd. It's odd in this case. So that means the ends are going in opposite directions. And then we have to look and see if the leading coefficient is positive or negative. Since it's negative, we have a decreasing function overall. It does some ups and downs in the middle, but it's starting high and ending low. Kind of didn't give myself room here. Here we go. So if that's the case, when x is going towards infinity, positive infinity, what is our function doing?
Going to negative infinity.
Exactly, it's going to negative infinity because it's going down on that right side. And how about if x is going to negative infinity?
Positive infinity.
Yes, exactly. Since our function, as we move to the left, it's going up. And we can
assume that it's opposite of what the infinity is.
Can you say the first part of that again? I missed the beginning.
Is it safe to assume that since it's the limit of infinity, that it would be the opposite? Oh no, because it's based off of the coefficient.
Yes, exactly. It's based on the coefficient. So since it's negative, they are opposite. Although if we go back to this graph that we started with on this one, this we don't have the equation for, but this one would have a positive leading coefficient since it's going up overall. So this one did have positive infinities together and negative infinities together. And we can look at the graph of these real quick just to confirm what we're seeing.
Real quick, so
Yeah.
the leading coefficient being negative 2x to the 5th power, we're looking at the negative in front of the 2, right? That's where we get the up and down.
Yes, exactly.
All right.
So the 2 itself doesn't have anything to do with it. It's just the negative part.
Okay.
So this is the graph of the function that we were just looking at. So negative 2x to the 5th plus 3x squared. So we can see that the left side of the graph is going up and the right side is going down. So as x gets bigger, if x gets closer to infinity, the function itself is going down towards negative infinity. Whereas if x is going to negative infinity, the graph is going up to infinity. So it's kind of like overall this graph has a negative slope. As x gets bigger, y gets smaller. And we could look at the other one. So we had 5x to the fourth minus 2x as our other one. Just take that away for a second. So this is 5x to the fourth minus 2x. So it's kind of weird looking in the middle, but we can see that both ends are up. So whichever way we're going in the x direction. And if we just decided to change this leading coefficient to a negative just to see what happens, now both ends are going down. So in that case, both sides would be going towards negative infinity. So what's happening in the middle doesn't matter. All that matters is what's happening on the ends of these functions. The thing we really want to know about, though, with limits at infinity is rational functions. So horizontal asymptotes have come up today, and that is going to be a big part of these. So on your review homework and what we did last week, you did some practice in finding horizontal asymptotes, and that is all of that stuff is going to be relevant here too. Before we get directly into the horizontal asymptotes though, I want us to just think about this limit. Not necessarily thinking about the graph, but just thinking about what's happening on this limit. So we want to know the limit of 1 over x when x gets close to infinity. So x is getting close to infinity on the whole real line. But if we just start to think, when x is 1, we have just 1 over 1, which is 1. When x is 2, we have 1/2. When x is 3, we have 1/3. When x is 4, we have 1/4. If we skip some, when x is 100, we have 1/100th. When x is 1000, we have 1/1000th. So each of these values, the value of 1 over x, is getting smaller and smaller and smaller as x gets bigger and bigger and bigger. So what is this eventually getting closer and closer and closer to as x gets bigger?
0.
0, exactly. Since as the denominator gets super big, the whole value of 1 over x is getting super small. So this is, oops, this is getting close to 0. This is a limit that we, kind of gives us an idea of what's happening when we have limits as x goes to infinity. There's no specific way to calculate this. It's just a conceptual thing we have to understand. If the denominator is getting super big, the whole value of this fraction is getting super small. And we know that if we were to graph 1 over x, it would also have a horizontal asymptote at 0, since the degree of the denominator is bigger than the degree of the numerator. So that idea gives us how we can think about slightly more complicated rational expressions, rational functions. So here's our next limit. So you actually already know how to figure this out. When x is getting super big, off to infinity, what is this function doing? What do we have?
Bigger numbers.
Not quite. What is the horizontal asymptote of this function?
Is it 0?
0, yes. So on this one, it's not 2 because the degree of the bottom is bigger than the degree of the top. So if those were the same degree, then it would be 2 because we would take that 4/2, which we will get to. But in this case, since the degree of the bottom is bigger than the degree of the top, our horizontal asymptote, that's not even close to the spelling, is at y equals 0. That's actually all we need to know to find this limit. Because as this function goes out off to infinity on the x-axis, the function itself is getting close to 0. So the horizontal asymptote is actually the limit as x goes to infinity. So this function, whatever it's doing, I don't know what it looks like in the middle, but it is getting close to 0 when x gets close to infinity. And that is because the degree of the bottom is bigger than the degree of the top. So this is our first case. The degree of the bottom is bigger. This always means that the limit as x goes to infinity of our function is equal to 0. For the same reason that we have a horizontal asymptote at 0 in this case, because the bottom is bigger than the top. And it's actually true that the limit on the other side, if x is going to negative infinity, we still have 0. So I'm going to scroll back up for just a moment. On this first example, we saw that the denominator was getting really big and the numerator was just 1, so the whole thing went to 0. The same thing is actually happening here. Even though the numerator is also getting big because it has some x's on it, the denominator is getting big faster. So we actually have sort of more complicated case of this same thing up here. The denominator is growing super fast and it's growing a lot faster than the numerator. So the denominator gets so big that the entire thing just turns into 0. So this is where this, you know that the horizontal asymptote is 0 when the degree of the denominator is bigger. And this is why. This is the calculus definition of a horizontal asymptote.
Real quick. So I understand the first part with the limit function equals 0 when x is approaching infinity. But the second part of it, when x is approaching negative infinity, it's going, on the one he drew anyways, it's going up.
Oh, that's just because I didn't do a good job of drawing it.
Okay.
This has some sort of vertical asymptote also in it, but the
Okay.
other
All
side
right.
would
Yeah,
be
I got you.
doing
That
something
makes
like
sense.
that. Yeah, it was just a bad drawing.
I got you.
So the horizontal asymptote and vertical asymptote are totally unrelated. Horizontal asymptotes, all we care about is those ends. So knowing that really what we're looking at when we look at limits as x goes to infinity is horizontal asymptotes, let's look at this next example. So in this case, what would the horizontal asymptote be from this function?
One half.
1/2, exactly. So that comes from, since these have the same degree, x to the third and x to the third, we're looking at just the leading coefficients. So we have 2/4, which reduces to 1/2. So what do you think the limit is as x goes to infinity?
A half.
Yes, exactly, 1/2. So that horizontal asymptote is telling the function what it's going to do as the two sides go out to infinities. So if the function grows a bunch, it will level out around the asymptote at 1/2.
Is it safe to assume that your horizontal asymptote is always the limit of the function?
Yes. If there is a horizontal asymptote, it is the limit as x approaches infinity.
And that's the same for the vertical asymptotes as well, right?
Yes, so the difference on the vertical asymptotes is that the x is approaching a specific value and the y is going to infinity or negative infinity, whereas this case it's sort of flipped. Now x is going to infinity or negative infinity and y is going towards a specific value.
Thank you.
In both cases though, yeah, the asymptote is the place where the limit is happening. So in this case, the case 2, we have the same degree on the top and bottom. Which means and this one is a little bit more awkward to write, but it's the ratio of the leading coefficients. So we get to completely ignore everything in the function except for those leading coefficients, which in this case is 2/4 or 1/2. And I'm going to actually put a plus or minus on this infinity on the limit because it's the same, oops, for whether it's a positive infinity or negative infinity. If we think about this in a similar way as we were before, in part A, when the degree on the bottom was bigger, that meant the bottom of the fraction is growing a lot faster, so the whole thing goes towards 0. In this case, the top and bottom are growing at the same rate because they both have the same leading coefficient. So they're both growing together, which means that all we care about is that the top has a 2 and the bottom has a 4. So all of these come from the relationship between the top and bottom as x gets bigger. And those powers determine that growth. So we have one more case. And so in this case, we're going to look at the x going to positive infinity and x going to negative infinity separately. So here we have the case where the degree of the top is bigger than the degree of the bottom. What is our horizontal asymptote in this case?
There isn't one.
Yes,
Define
exactly. Yeah, there isn't one. None. So in this case, we would have something like a slant asymptote or an oblique asymptote, which you're not going to have to find in this class. But the point is that the ends are not going to be leveling off into some nice number. They're either going to be going up or down to infinity. So this is another case where we can look at a graph to determine which way our ends are going. Let me see if I can copy and paste this into Desmos. That'd be nice. So this is a super weird looking function, but that is okay. And actually, there it is, okay. A oblique asymptote is that line that's creating a new asymptote. So it's going diagonally. So all we care about, we're not focusing in on what weird stuff is happening in the middle. All we care about is what the function is doing as x gets really big and x gets really small. So what is the limit of the function as x goes to infinity in this case?
Infinity, positive infinity.
Exactly. Since this right side is increasing, it's going up to infinity, positive infinity. And how about when x is going towards negative infinity?
Negative.
Exactly. So this left side is going down. So that's all we need to know. So I'm going to draw a very rough sketch of this in the notes so we can just have an idea of what we're looking at here. So there was some sort of vertical asymptote happening, which we're not focusing on right now. But basically this side was doing something like this, and this side was doing something like this. So all we care about is these ends. When x goes toward infinity, this right end is increasing. When x goes towards negative infinity, the left end is decreasing. So we will say this one is infinity, and this one is negative infinity. It's kind of squished. So if we don't have a horizontal asymptote, we can graph it just to see if the ends are increasing, or case where for a rational function where the ends are when when the function is going to infinity or negative infinity, when x also is. So this is our third case, and this will be the very last thing that I write for the day. Case 3 is the degree on top is bigger. So the limit is either infinity or negative infinity. And that's because the top is growing faster now. So the bottom can't keep up. So the top is getting really big, and the whole thing either grows to infinity or to negative infinity. My slower clock says it's 1:15 now, so that probably means it's actually 1:16. It is. So that is all of our time for today. If you have any questions, I can stick around for a few minutes, but otherwise I will post the rest of homework 2 in a little while, and I will see you next Tuesday.
Thank you. What are your tutoring hours for the rest of this week, or do you have any?
I have office hours by appointment on today from 1:30 to 3. But I'm also open to making other appointments if you want to email me with other times.
Okay, perfect. Thank you so much. I appreciate it, Madeline. Have a great
You're
day.
welcome. You too.
Bye.
Bye.
Thank you. Have a good weekend.
You too.
Thank you.
Thank you.
Thank you. Good afternoon.
You too.
Thanks.
You're welcome.